All right, so we're going to look at a few more of these from 11.5. I think I'll do a few more, and that will be the last video for this section. All right, so on number 7, it's a little hard to see, but yeah. All right, so on number 7, we got these 15 transistors, 4 of which are defective. The question is, if 4 are selected at random, find the probability that either A, all are defective, or B, none are. Okay, so we got to take both of these cases individually. So in order to choose the 4 transistors from 15, that's what we got to do first. Okay? So the number of ways to choose the 4 transistors, defective or not, from 15. Probably should be able to recognize that as 15 choose 4. Let's do that first. That's going to be a number. So let's see. 15 choose 4. 1365. This is going to be the number on bottom, and this is the denominator. When we get to our probability. Okay, for part A, for the top number, we want to choose all of the defective transistors. Well, there are 4 defective ones, and we're choosing 4. So the defective ones would be 4 choose 4. Obviously, if we were able to choose them all, that would be only one way to do that. So the probability of all defective is 1 over 1365. So that's the number that we would type into MyMathLab. Okay. On part B, we only want good ones, or ones that are not defective. So none are defective. So what we have to do is take our total transistors, and we have to subtract off the 4 defective transistors. And there are 11 good transistors that we can choose from. Okay, this means these 11 are not defective. And so the way we could choose these, so we want to choose 4 of these not defective ones. So 11 choose 4. Okay, we can type that in. 11 choose 4. 330. So this is the number that will be on top. Okay. So the probability that none are defective is 330 over 1365. Now, if I'm lucky, I can type this number in and then push the button on the calculator. Okay, so I get a decimal, of course. second PRB, and look, it even gives me the reduced fraction. 22 over 91. So this is what my math lab's going to want. All right. So that's number 7. I'm going to look at number 8 next. All right. Number 8, we have a city council of 5 Democrats and 7 Republicans. If a committee to select some of these people are made, how can we do that with 2 Democrats and 5 Republicans? Okay, first I need to know the total number of ways to choose my committee. My committee has to have 7 people, so 7 people on the committee. Out of the total, which in this case is 5 plus 7, which is 12. So 5 Democrats and 7 Republicans, which is equal to 12. Okay, so this is the number that we're choosing from. 12 choose 7. This is to get the number on the bottom. Okay. So 12 choose 7. If I type that in, 12 choose 7, I get 792. That's our denominator. Now the question is, this particular committee needs to have 2 Democrats and 5 Republicans. Okay, how to choose the 2 Democrats and 5 Republicans. And here's how we do that. This is another blank problem with the combinations. So for my Democrats, for my Republicans, if I look at the question again, I see that I've got 2 Democrats that I need to choose from, and I have a total of 5 Democrats. So 5 choose 2. And for the number of Republicans, I have 7 Republicans. 7 choose 5. Okay. So this is all I've got to work out. So 5 choose 2, 10, times 7 choose 5, 1, which is 210. So the probability that we're looking for, let's see. So the probability of 2 Democrats and 5 Republicans is equal to, this number is on top, 210, divided by this number here, which I said earlier was our denominator. That's the total number of ways to choose. So 210 divided by 792. I'm getting to this decimal again, but remember I can do second PRB, and if I'm lucky, it'll fix it. Okay, 35 over 132. All right. Okay. And so now I'll look at number 9. Number 10 is very similar to number 9, so I'm not going to do it. I'm going to do number 9, and then after that I'll do number 15 because it's a little tricky. Number 9, we are playing a game of cards in which we're dealt 3 cards. So the first question is, find the total number of possible 3-card poker hands. Well, okay, all right. Total number of 3-card poker. Well, that means we have 52 cards, right? We're going to choose 3 of those. So 52, choose 3. I did an example similar to this in the notes for 11.3, where I chose how many 2-card hands could I have. It's basically the same thing. I'm just changing one of the numbers. So that's the total number of hands. That's going to be our denominator on some of these. Okay, that's all the possibilities that I got. In part B, it wants to know the heart flush. All right, well, let me show you what a heart flush is. And it kind of tells you in part B, but this is an example of a heart flush. Okay, meaning I got 3 hearts in a row. I'm sorry, not in a row, just 3 hearts. Now, the tricky thing about this particular problem is it does not distinguish between a heart flush and a straight flush. Let me explain what a straight flush is very quickly, especially for those who are familiar with poker, like myself. You would probably be tempted to, distinguish the two because they are different, especially if you play this at a casino. This is an example of a straight flush because it's 3, 4, 5 all sequential, whereas this is not a straight flush because there's a big break there, or a break. Okay? Most of the time we would separate this because that's a straight flush versus this. Okay, in this game, on this, they do not distinguish it. So, all right, that was a bit of a tangent, but that means that if I don't care about sequentialness, then any combination of 3 hearts is a flush. Therefore, since there's a total of 13 hearts in the deck, remember, there are 13 hearts in a deck. That means 13 choose 3. Let's do that. 13 choose 3. 286. And on part C, they want the probability. So in part C, the probability of a heart flush, which just means I take this number, put it over that number. Okay. In fact, this probability of a heart flush is the same as the probability of a club flush or a spade flush or a diamond flush. Because that's a 6. In this one, notice they want you to round to 6 decimal places, which means I don't have to simplify my fraction. 286 divided by 22100. So you can see that. All right, let's see if you can see that. I'm going to write out this decimal. 0.012941176. That's what I got on the calculator. 012941176. They want us to round 6 decimal places. 1, 2, 3, 4, 5, 6. Since this number here is less than 5, my final answer will just be that. 1, 2, 3, 4, 5, 6. Okay. So that is number 9. And the last one we're going to do for this video is number 15. That's the only other one I feel like will give you some trouble. These here are from notes or from the book. Okay. So number 15. They're going to have similar questions to this in the homework. If yours is not exactly the same as this, it'll be very similar. So the digits 2, 3, 4, 5, 6, 7 are randomly arranged to form a 3-digit number. Okay, so that's important. 3-digit number. Okay. Arranged to form a 3-digit number. Find the probability that the number is even and greater than 700. So first, step 1. Find all possible 3-digit numbers with those digits. So I'll just write them out. With 2, 3, 4, 5, 6, 7. Okay. The way this works is I'm going to come down here and make my 3-digit number again. I can put, which numbers could I put here? So this is the first digit, second digit, third digit. I could put 1, 2, 3, 4, 5, or 6 possible numbers. So it's actually 6 times 5, because if I put 2 first, now I could put 5 numbers. If I put the 3 next, then I have 4 left. So this is a permutation question. I find that it's easier with just the blanks, if I think about it like that. So 20 times 6 or 30 times 4, or you can do 6 times 5 times 4. So this will be the top number. This is the numerator. Nope, I'm sorry. This is the denominator. That's all the possibilities. Now it says we're trying to find a number that is even and greater than 700. Step 2, even and bigger than 700. So there's my digits again. If I'm going to make a number that is bigger than 700, given those digits, it must start with 7. Okay? This must be, so this is my first, second, third, so it must be 7 for the first position. I have one possibility there, okay? Now let's use the fact that it must be even. If a number is even, then it ends with an even number, 0, 2, 4, 6, 8. Okay? So even means it must end with 2, 4, or 6, given the digits I have in this problem. So I have 3 potential candidates for the last number. Okay. Now here's the thing. I've chosen a number here, and even though there's a number here, I've only chosen 2, 4, or 6. I just put one of those there. which means I still have all but this 7 and one of these, and I still have 2 of the even numbers. So let's say I put a 6 in the last spot. I still have 2, 3, 4, or 5 that I could choose from. So that is why this is a 4. Okay, that's the trickiest one part for me. So the probability of running out of space on this paper, so I'm just going to put probability equals 12 over 120. The probability is 1/10. Okay, so yours is going to be similar. You may have more digits. This number is going to probably be different, but it'll work the same way.